Good evening, everyone. Good evening, sir. So, I welcome you to this fifth session of our World Space Week event. And I hope you guys are enjoying this series of events we are having. Okay, like from the Building Your Space Club, we are reaching to the Mars. Okay, so this is really a fascinating journey. We have gone through the Indian astronomy, we have gone through the astrobiology. Now we are going to learn the aspects of geoscience with respect to the our planet Mars. Okay, so today we have our keynote speaker as Dr. Priyabrata sir, who is currently assistant professor in this Parul University of Geoscience. He has been a director of IIRES, okay, Institute of Innovation, Research and Education for Earth. Okay, this is the initiative which is taken by sir. Okay, and you can find on Google and YouTube. There is a series of lecture which you can find, okay, on this particular channel. And further, he has been a research associate with the RLI Physical Research Laboratory, which is a chapter of ISRO, and he has done his doctorate from the Hiroshima University. Okay, so yeah, he holds a really great experience in this particular field. So today he will be giving you his experience in this field, geoscience, and yeah, to the planet Mars, which we all aspire to live someday on the planet Mars. Okay, so over to you, sir, and all the best, sir, for this particular session.
Thanks for nice introduction. It's my pleasure. Thanks for inviting me. So I from last 2.5 years, I am actually involving in the science communications and regularly organizing different lectures. So it's a great pleasure. so without wasting much time, actually, I'd like to start my today's talk. Okay. So I think shall we wait for another 1 or 2 minutes, or we'll start?
So you can start. I think audience is there almost.
Okay. So, okay. So today's topic is actually I have selected on basically geoscience quest to reveal the mysteries of Mars. So why this topic? Because nowadays this space is always very enthusiastic for everyone. Since when you came to know about different planets and planetary bodies. Okay, since my childhood, I have a keen interest to understand, and I think everyone have an interest. So, but especially after completion, my working on this Mars and all this thing. Actually, this thing actually came after completion of my PhD. Before PhD or during PhD, I'm completely an art scientist. Okay, so first I learned my degree from in geology, bachelor's and master's in geology from Calcutta, Presidency College, Calcutta. Then I got a PhD from Hiroshima University in Earth Sciences only. Then after the completion of my PhD, one day I got a paper from my friend, a senior, you can say. He shared one PDF to me. Thus, you read this one. It's a very nice thing because at that time, in 2013-14, that time this curiosity rover landed on Mars, and the first publication came out from the Mars by the paper was written by John Gotzinger, and on the paper he has mentioned that they found a fluvial conglomerate. Okay. And all sedimentary structures, different kind of, and they show beautiful outcrop images, outcrop photographs of Mars. So that's the turning point, I actually can say. When I was reading that paper, I decided, okay, if I get the opportunity to work on this topic, definitely I will do. Then I started actually shifted my career towards this planetary science. I got an opportunity to work on initially on Martian meteorites in PRL Ahmedabad. Then got an opportunity to work on different topics like in Martian modern Martian climates and water rock interactions, then ancient climates and sedimentation system. This kind of study I mostly done. My specialization is on sedimentology. Okay, so now what actually planetary scientists actually do? What is planetary science? Planetary science is a study of a planetary system or a celestial body. Okay, and it's a highly interdisciplinary field of study, including all aspects like astronomy, astrophysics, then atmospheric science, geology, space physics, biology, chemistry, etc., etc. Okay, so in planetary science we work together. Okay, all this discipline, and in this while this study all this topic, geology is one of the key or important part. Okay, so what we actually do, the scientist or the researcher, we actually collect the information. So, like, see, this is the diagram. Okay, these are all the scholars or scientists. They actually collect the information, and we actually build our knowledge base. This is our knowledge base. Okay, so we collect information for a particular planet or planetary bodies. Okay, their physical information, the chemical information. Okay, the biological if possible. Then other sort of information. Okay, then we develop this kind of knowledge base. So this is our this is what we actually do. Scientists actually do. Okay, so what we means our geologists, what we do actually, we are mostly working on the planetary systems. So what is planetary systems? Planetary systems are basically suppose if you consider this as a planet. Okay, and it's have a layer like a core, mantle, and crust. Okay, like Earth have a inner core, outer core, then mantle, then crust, and everything. Okay, so now if we want to subdivide this our planet, we can subdivide this thing into two major group. Okay, or two major part. One is the surface. Okay, or the upper layer. Okay, that contains atmosphere. Then hydrosphere means ocean, lakes, and all this thing, water bodies. Okay. Then cryosphere. Okay, the cryosphere means the glaciers. Okay, and biosphere. Biosphere is especially for Earth. Okay, so these are the system that is operative on the surface of the planet. Okay, and these are the system like lithosphere, atmosphere, mantle, then geodynamo. All these things. These are actually internal part or internal processes of Earth or say the planet. So now, if you consider these eight processes are major dominating process that is actually operative on in any planet, and it's mostly on Earth, not any planet, mostly on Earth. And what we do actually, we actually try to understand the interaction between these processes, like interaction between the hydrosphere and cryosphere, or biosphere and hydrosphere, then hydrosphere and lithosphere, okay, asthenosphere and lithosphere, the interaction between these processes. And our expertise is, as geologists, we are expert on this study of this interaction. And also what happened in the past means it's not like that like a few years back or a few hundred of years back. Our past is like billions and millions years ago. So what happened on that planet? How this processes or the systems was working billions and millions years ago. Okay, so that's why we need a specialist, and geologist or geoscientist are expert on doing this or reconstructing these processes. So now, based on this. Processes like major process like volcanic process, then tectonic process, okay, volcanic, tectonic, and like surface process like fluvial, atmospheric process. You can subdivide or you can classify our terrestrial planets or terrestrial planetary bodies, okay, into like this. Okay, so for example, like Io is a satellite. Okay, then Mercury, then Mars, then Earth. Okay, you can see some Earth is active in both, like volcanism also here. Okay, then it's active in tectonics. Okay, and also have atmospheric processes. Mars is here. Mars is active, but not that much active like Earth. Okay, then Venus is hyperactive in terms of volcanic. Okay, then also have a bit of tectonic activity. Then atmospheric process. So like this, we can classify our or this terrestrial planetary bodies. Now see, moon is here. Moon was active, volcanically active previously, but right now it doesn't have any tectonics or any atmosphere. So however, it is active in terms of volcanic process, but it is not that much active or not active in atmospheric and tectonic process. So this diagram is very fantastic, and you can easily figure it out because this is important. The understanding of this process is actually important to understand the complexity. If you are looking for searching for habitability or life, then our target should be like active planets. Okay, because the active planets, active means I'm talking about these three component. Okay. Those planets are mostly feasible or preferred area where you can get the complex chemistry and complex things. So complex chemistry means that complex chemistry actually help to trigger the origin of life. So that's why in that sense also it's very important to understand this geological processes. Okay, so now what we exactly do? We actually read the rocks. So this is one, suppose it's a cartoon diagram. Okay, this one is our, I can say, a mountain, then a fluvial channels, a river, then the delta, then this part is lake. Okay, and what we do, we actually collect the information from the sediments. Okay. So I'm a sedimentologist, so my expertise in this. Okay, so what we do actually, we actually read the rock layers. So rock for us, the rock layers are like these book chapters. So these are different type of rock layers. Okay, so this is a popular cartoon that actually is one of my junior. Actually, he is a very good cartoonist. Atanu is now in Baba Cartoon Center. He actually draw this cartoon. So I'm thankful to him. He's a very good cartoonist. Actually, he's a geologist and also cartoonist. So so this is the rock book, and we actually study all these rock layers like a book chapter. So for example, this is one outcrop or a hill near in Kutch region. Okay, so for non-geologists or those are not related to geology fields, for them it's like a mountain or like a hill, and but but you can see some layers are present in this hillock. Okay, so and for us it's not like that. For us it's like that you can subdivide this entire litho unit or rock layers into different intervals. Okay, so for us this is like a chapter 1, this is chapter 2, and this is our chapter 3. Okay, now if you zoom it this portion or some other portion, okay, then you can see in this part right side, you can see. So there's a color difference between this chapter 1 and chapter 2. Okay, so the layers of this chapter 1 are more grayish. Okay, however the chapter 2 is our more yellowish or brownish in color. So, okay, so that means by looking that the texture and the structure, or you can say by depositional features, okay, we can easily separate out the internal based on the internal structure. You can separate out the sedimentary rock layers. Okay, and we can see something. Okay, this may be a product where we can get a different kind of elements or a chemical composition compared to this. So these two are chemically separated. Okay, so that's why it is showing this kind of color change or you can say lithological changes. Suppose this part is more clay dominated or mud dominated. Okay, however this part, the top part, is more sand dominated. So this clay dominated means that it indicates a clay actually deposited in a low energy condition. Okay, in lower energy conditions. Okay, so this mud are precipitate. Mud are finer grains compared to sand. Sand are more coarser. So mud actually deposited in a low energy condition compared to sand. So this indicate actually a change of energy condition. So earlier it is a low energy condition. Then with time means it's deposited earlier, and this one is deposited later. So it's with time it actually is showing some change of energy condition. And this is And we are the expert. Actually, we try to reconstruct what are the causes behind that. Why this energy condition shifted? Okay, what happened at that time? Why this thing happened? Okay, so earlier it was like a, for example, it was like a lake or maybe a marine condition. Then maybe with time. We may get a fluvial or maybe deltaic sequence after that. So, so in a place where earlier was a marine, the next time we get after a few million years, we may get a fluvial sequence. So, what causes that thing? So that is the part actually we study in geology, the natural phenomena. Okay, through the understanding of these rock layers. So these outcrops and these rocks are basically for us it's like a laboratory. Okay, so and we frequently visit a field to understand all these changes. Then we collect samples from different rock layers, and we do petrography study, means to confirm the rock layers. We study the minerals and rocks under microscope. Okay, then sometimes we use geophysical study to understand the subsurface condition. Okay, then the chemical changes, the elemental variation. Okay, and also we use isotope study to date the rocks, or sometimes you can check the isotopic behavior, change of isotope behavior with time, respect to time. So these are the most common processes that we are using. Other than this, also there are several other processes that we are using, but these four are more common nowadays. Okay. So and through the study we can understand the depositional or the formation or evolution of rock. So now coming to the planetary science. So earlier I told what we actually do, a geologist on field or in laboratory. Now what is the key agenda of a planetary science? Suppose if someone have expertise in geoscience and want interested to do planetary science. Okay, so what are the major agendas? So major agendas are basically two. One, the major agenda is to understand the origin of evolution of a solar system. Means if we you can subdivide our you can divide our entire scientific community, planetary science community, into two different types. One community is actually working on to understand the original evolution of solar system. Means mostly the formation of the planets and planetary bodies. Then pre-solar materials also sometimes. Then the initial formation of the protoplanets. Then after forming the planet, the changes, the internal changes, the magmatic evolutions, then the surface processes, then the tectonic process. So these are the part that is comes under the original evolution of solar system. And the second part is that original evolution and limits of life, means in terms of astrobiology. Okay, so I think Shiv Shankar Palit has given one fantastic lecture a few days back. I think you have attended his talk. So this part comes under that astrobiological point of view. Means whether is there any condition other than Earth where life was occur, or the conditions, the test of, or you can say we are trying to test the conditions, the habitable conditions, whether that planet was habitable billion years before or not. So this part is actually that part, or astrobiological part, or original evolution of limits and life. So now I'm coming to Mars. So Mars, for those people who are very new in this subject. So for that, I can show you this is a molar image of Mars, or Mars elevation. Okay, so it's an elevation map of Mars. Okay, so you can see this. You can see this. The southern hemisphere of Mars is elevated compared to this northern hemisphere. Okay, so northern hemisphere actually it's like a lowland. Okay, and all this northern part is less cratered compared to southern hemisphere. Southern hemisphere is highly cratered. You can see multiple craters here. Okay, but northern hemisphere is less cratered. And also you can see some volcanoes. These are extinct volcanoes. Means the volcanoes were was active millions of years or billions of years ago, but it is not active right now. But we have traces of volcanic activity, so that's why we can say that the planet was active. Okay, it's not currently we are not sure whether is there any volcanic activity, but a million years before the planet was active. So here also we can see volcanic activity, and few volcanic activities also present here, and a piece of rift valleys and a kind of extensional features or fractures. This kind of features also present on Mars. So in terms of this rifting also means some fracturing also present. So so this morphological study also we can say the planet was active. Okay, so if the planet was active, then there must be something more also. So that is the catch. Okay, so if the planet was active, that means that the planet had atmosphere also earlier. I think in early history. So what are those? What are those activities? So now, if you see the geological history or geological time scale of Mars, the initial period of Mars, okay, it is a Noachian period. In Noachian or pre-Noachian, that time period, Mars was hyperactive, active in the sense of volcanism. Okay, then water activities. Okay, then other processes was active in this Noachian period. Then Hesperian period also Mars was active in terms of valley networks. Okay, so water was there at that time of Mars in Hesperian, Amazonian, Noachian and Hesperian period. Then with time, after Hesperian, all these activities was actually decayed down. Okay, and slowly everything was gone. So it lost. So maybe because of this magnetic field or the internal dynamo, or something happened after that, means after Amazonian or after Hesperian period. So, but we are now very much sure that the planet was active long back. So that means there was a volcano, then atmosphere. Okay, proper atmosphere that can sustain liquid water on the surface. Okay, and if there's a liquid water, then there may be a chance of something more interesting. Okay, so now if you see this plots or map, this is the elemental map of Martian surface. So this is silicon map of surface, and this is magnesium map of the surface of Mars. And here also you can see the inhomogeneity that is present on the surface of Mars. So this inhomogeneity actually it's good for habitability actually. So it is not homogeneous. Okay, so if this is homogeneous, then kind of monotonous thing. So the chemistry will be simple, but in terms of chemistry of Mars, it is very complex. So the complex chemistry actually good for habitability. So, but if you see now if you characterize the elemental composition, okay, for example, this potassium and sodium, this total alkali versus silica, the average composition of this Martian crust is actually basaltic in nature. Okay, so mostly you can get basalt on the surface. Mostly the crust is made up of basalt. So now I'm coming to the first slide, the previous slide. Okay, so I'm working on this interaction between this hydrosphere and lithosphere right now. So hydrosphere means Martian hydrosphere, and lithosphere, Martian lithosphere. Okay, so and it's very interesting to understand the ancient or early evolution or early or that time ancient hydrosphere and lithosphere interaction. So how we actually do this kind of study, sitting in India or for any places. So for that, if you do this hydrosphere and lithosphere study, so ultimately what you get, what the information you will get if you do this kind of study. So the information if you'll get mostly the study is called water rock interaction. So if you do the water rock interaction study, of any planet, then you can actually get two different products. One is soil that is formed due to the weathering. Okay, means the soil forming process, and another product that you'll get that is sedimentary rock or sedimentary under the sedimentation process. So in soil, if you study soils or the weathering product, so you can subdivide this weathering product into two different parts. One is physical weathering and another is chemical weathering. So if you study this physical weathering, then you can understand the mechanical processes, like how these rocks are actually degraded. Okay, so this mechanical impact cratering, and then frosting, then snow, all this. But if you study this chemical process, means how this material actually altered or weathered under water related process, then actually you can reconstruct the climate of the planet at that time. It's okay, because that water that it actually act like an agent. Okay, and that actually help to degrade or dilute different minerals that is present on the host rock. So if you study this, the chemical behavior or chemical thing of this weathered rock or soil, then actually you can get to know about the climates and the atmosphere, then groundwater, and ultimately it helps to understand the habitability. Okay, so this is that very interesting part of water in rock interaction study. And if you study the sedimentation part, means that after the erosion, then transportation, deposition, and liquefaction, this part will help to understand the physical process, like say for example the alluvial fans, rivers, and delta, all this process. Okay, how the surface was actually curved by this sedimentation or water bearing process. And also some chemical information, like say if you get some carbonate or evaporites or banded iron formation kind of thing, then also you can understand the seawater chemistry or lake water chemistry, and through that also you can understand different climatic or hydrological changes, and that also help to understand like hydrosphere, atmosphere, lithospheric, then biospheric interaction, obviously, then the flow process. And also it helps to understand or you can get some information about the economic resources. Means the sedimentary process actually helps to it actually concentrate some elements. Okay, so maybe those elements are economically viable. For example, BIF, banded iron formation, is a sedimentary deposit, and it's a major source of iron on Earth. Okay, so if you study this, then limestone is also economic mineral for Earth. Then evaporites. Okay, but limestone is not present on Mars at that much amount, but definitely evaporites are there. Okay, you can get evaporites like gypsum salts. Okay, then iron. Okay, this kind of minerals are present on Mars. So we can use that mineral. We can use those resources for our future missions. So that for that purpose also we can study all these sedimentation process and weathering processes. So now, what are the resources? Resources means what kind of resources we can use to understand to reconstruct all these things. So right now we do not have any direct samples. Means that we do not have any direct samples from Mars, but we have meteorites. Meteorites are naturally they came from Mars by natural processes. Or like mostly we have meteorites from asteroid belts, but also we have some meteorites from Mars, and we categorize those meteorites called SNC meteorite or Sergoti, Nakhla, and Chasigney. These three type of meteorite we have right now on Earth. Okay, and if you study all this meteorite, then also we can say something about Martian geology. Okay, so these meteorites are very important for us. And then second source of information is the orbiter. That orbiter means the satellite that we actually send to Mars in different time by different space agencies on like NASA, ESA. Then our India also we have MOM mission, orbiter mission. Okay, then lander and rover missions. Okay, so these are the main source of information or instrument, or what you can say. These are the main resources that from which we can collect, we can gather the data, and we can interpret all these things. So now I'll talk something about the Martian meteorites. Okay, so for example, if you study the water rock interaction using Martian meteorite, then the meteorite named Nakhla is very important. Okay, so Nakhla is a type of meteorite that contains clay minerals inside. So this is a polished section, or a thin section of that material called Nakhla, or it's actually laphite. Okay, it's a group of Nakhla mineral, Nakhla meteorite, and within so this is olivine grain, and within that olivine grain you can see this kind of veins. These are veins, and these veins are actually contain some minerals that we call edensite. The edensite is usually secondary minerals. These secondary minerals actually formed due to the alteration process, means the water-related process. So, suppose if you put water on, or if this material, or this Nakhla, or this material, if it was under interaction, or at the presence of water, if the material was there, then with time, what will happen? This it creates some fracture, and within this fracture, this clay minerals actually precipitate. Okay, so these are the clay. Okay, and this clay actually indicates the presence of waters. Okay, so without water, it is not possible. So this is the first source of information actually, from which actually came to know that Mars, Mars was affected by liquid water, and we can study these rocks under laboratory. So we can do n number of analysis, both chemical analysis, mineralogical analysis, and isotope analysis. Whatever we want, we can do. We can study. Okay, but the limitations are samples are very limited. Okay, so you'll not get a huge amount of samples. So meteorites are very small. So these are the limitations. But however, we can understand the different water rock interaction to studying these sections. Okay, so this is the clay minerals. Okay, and mostly FEMG clay, smectite kind of clay. Then we have another data set. They're mostly orbiter, and from the orbiter also we can we came to know that Mars was basically flooded, means plenty of water was there on the surface, and due to this water you can see beautiful delta. This example. Okay, so this kind of deltaic deposit actually form on the surface of Mars. So this is not one event, actually it's a multiple event. So this layer was formed actually earlier, then the later this layer formed. Okay, so this image formed. So, and if you zoom at this part, you can see this meandering channels. Okay, this is the point where or the lateral accretion of these channels. Okay, it's very common. It's very similar like Earth river system. Okay, and most importantly, by studying only by visual only, it is not possible to conclude whether this feature was done or generated by water influence. It is not sufficient. So we need a mineralogical study. So if you check the mineralogy of this area, for example, this is the CRISM map. Okay, our hyperspectral mineral map. So in this CRISM map also we can got some clay minerals here. So then we can conclude that, okay, if we are getting clay, that means this product actually deposited by water bearing processes or fluid processes. So through this understanding also we can say that Mars billions of years ago, Mars had water on the surface. Now like this, people have spotted different locations where we have actually this sedimentary deposit. So this was a sedimentary deposit. This is sedimentary deposit, and And these are the places where we have sedimentary rocks on Mars. So then 2012 actually, NASA has planned to land on the surface of the Mars, and they have selected this crater called Gale crater. It's very important because inside this crater we have a thick pile of sediments that is almost 5 kilometers thick, okay, and contains sedimentary rocks. So if you study all the sedimentary rock inside this crater, so actually helps to understand the evolution, okay. So how this material actually deposited, and how the climate was shifted. So of course the habitability study. So that's why they planned the Curiosity mission, and the rover was actually landed here, okay, in this region. So yeah, this is that a view of Gale crater, and Mars Science Laboratory or Curiosity rover actually landed here, and it is now it's moving toward this side, and it has a plan to move up towards this Aeolis Mons, okay, or Mount Sharp region. So it's a huge scientific called program, okay, and the rover is still working there, okay, and while studying all this thing, while planning all this project, okay. So from the orbiter also we can study a different mineralogical or different geomorphological information using that your high-res data or orbiter data or mineral data. So from that also we can get some information, and we can actually guide the rover. We can design that rover direction or rover path based on the geological information that we are getting from the orbiter data. Okay, so this is the rover track. So rover was landed here. Then this part is a dune field. So they took a turn, then entered this side. Then it crossed that one ridge like feature called Vera Dubin's ridge. Then entered again a clay unit. Then now it's moving toward this side. Okay, currently it's now here. So this is a map. Okay, now okay, this is that surface view of image that is snapped by Curiosity rover. This is the our Gale crater rim. Okay, and this part is Vera Dubin's ridge. Okay, means this part. Okay, actually rover actually took the images standing here towards this side. Okay, so this is Vera Dubin's ridge, and this is the crater rim, and this part is your dune field, Bagnall dune field. Okay, and while traversing, it collects many information. One is images, different images, navigation camera image, then color camera images or must-cam image, then microscope or hand lens camera image called Mahali. Okay, this kind of images is taken by this rover, and while it is snapping the rocks or outcrops, it first observed this kind of pebbly sandstone unit or pebbly unit. Okay, and you can see multiple pebbles present in these rocks. So these pebbles are actually very common on Earth. Okay, and it is associated with river deposit. Okay, so by seeing also you can see you can tell maybe this rocks that is found on Mars is a product of a river deposit using this analog study. Okay, then the rover actually traversed down inside the crater and encountered different type of sedimentary rocks. So you can see these are all the sedimentary rocks. These are layer deposit. Okay, so and one layer is deposited another. So this is the older one. If you move towards this side, you may be actually traversing the time. Okay, this is older and this side is younger. So older to younger. So and you can say you can actually construct the past. What happened at that time? Okay, and what happened in this time. So it's very beautiful to understand all these things. So now it observed some other feature like evenly laminated deposit and unevenly laminated deposit, kind of sedimentary structure. Then some climbing, critically climbing, ripples lamination, then graded bedding, then pebbly sandstone, and from that people have proposed a delta or fluvio delta kind of fluvio-lacustrine environment in this region of this Gale crater. Then they have studied the lake deposit. They have found alternate banding or alternate layering of this lamina, thick lamina, then thin and thick lamina here. Then finally laminated this mudstone. Then some cross-stratified laminated cross-stratified mudstone or sandstone here in this region, and also observe a mud crack region. Okay, mud crack means this type of crack are actually formed desiccation crack, means when the surface of Earth or surface was exposed to the atmosphere. Okay, then this kind of fracture or crack actually develop. Most commonly in summertime also you can see some ponds or in lake this kind of fractures. So this indicate the aerial exposure. Okay, so earlier it was a lake, but lake was exposed to the atmosphere. So that's why this kind of fractures or crack develop state kind of condition. So lake level was fluctuating. Okay, so this indicate a fluctuation of lake level conditions. So that may be seasonal, like summer and winter or that kind of thing. I'm not sure. Then in some of our study also we have observed different the change in lamina thicknesses. So this is one laminated mudstone, and we also observed a variation of this thick and thin lamina, Okay, and also interestingly this kind of paired laminas. So this is if you measure all these laminas and if you plot this bar chart, then also you can see the changes. So this is the thick lamina, then this part is thin lamina, then thick lamina, then thin, then thick, then thin, then thick. So this thick thin pattern is indicating some changes in hydrological condition of the lake, and that these changes may be possible due to some astronomical cycles, for example lunar cycles, or maybe some solar cycles, seasonal cycles. We are not sure. Okay, so this type of change is also observed in the sedimentary rock record. So and recently one image that is came from Mars Curiosity rover, and it spotted one ripple marks surface, or rippled surface. You can see this is a ripple marks of Mars, and this is a ripple marks of Chandipur area on Earth. Okay, so they are exactly same. Okay, and these ripple marks actually formed due to this current or wave actions. Okay, so a similar type of ripple marks you can observe on Martian surface. So we have no doubt that Mars once had water, but yes, it was very active. Okay, and you can get different kind of sedimentary structures on Mars. So, but before we study all these things, the Martian geology, we have to have a solid understanding about Earth geology. So first we have to understand the geoscience part. Okay, so then only you can reconstruct the Martian scenario. You can actually figure it out. Okay, what is the formation, what is the geometry, or what is the sedimentary pattern? Okay, and what is the reason behind that? Means the processes. Okay, suppose if you got this ripple marks on the surface of Mars, then immediately if you study the Earth ripple, then you can easily reconstruct this ripple may be processed by or deposited by this kind of environment. Okay, so that's why it is very it's a much needed thing that before you enter planetary geosciences, first you have to have a understanding about Earth geosciences or geology. Okay, so after all this thing, people have proposed this kind of lake deposit or lacustrine deposit. Okay, on this, for this Gale crater region. Then they have collected different mineralogical information from these rock layers, and this mineralogical informations also indicate that the mineralogy of these lakes, these lake beds, are not uniform. Okay, so this early part, this initial part, or the bottom one, actually composed of mostly phyllosilicates. Okay, then some magnetite and all this thing. Okay, then suddenly in this part, this variable part, you got a hematite, high hematite content. Okay, then there is no hematite in this part. So then we got xerosite. Okay, so the occurrence of hematite and occurrence of xerosite are different minerals that actually indicate a change of redox conditions. Redox means oxidation reduction condition of the lake. Okay, so the mineralogical study also we can say the change in mineral the chemistry of the water that was there on the time of Mars, and what is the reason behind that? Why this chemistry was changing? It is because of geological process or because of biological process? Because we do not have any biological information or direct evidence of biological present, but or if you study the earth rocks, the formation of this hematite or all this thing, it is directly related to biology. Okay, so this photosynthesis, synthetic bacteria, all these things that actually help to precipitate iron at the ocean bottom or lake bottom. So this is very interesting. That's why this study of this geochemistry and mineralogy and understanding about this geochemical study and mineralogical study is very important. So what are the information right now we have on Mars about biosignatures? It's only this. Okay, so we have the chemistry, means a complex organic molecule like this kind of thiophane kind of molecule we have that is detected by Curiosity rover using SAM instrument. Okay, or GCMS. It's basically GCMS, gas chromatography mass spectrometer, and the mass spectrometer analysis. This thing came out, and it is related on Earth. This kind of chemicals can be found related to biogenic activity, or sometime maybe due to the abiogenic activity also. But thing is that we right now do not have any evidences of fossil form of life, like fossilized form. So we do not have any direct evidence of fossils. So the information we are getting from Mars, that is indirect, like chemical signatures, but not the form. So what is required, that is a fossilized evidence. Okay, so like this. So initially during the 70s time, we have for Mars, like for us Mars was like red planet. Okay, then after and in 90s and 2010, during that time, through the advancement of this technology, okay, we came to know that Mars was not dry. Okay, it was wet and humid in geological past. So this information we get to know during the 90s and 20s time, 2010, and in 2020 we got this complex organic signature on Mars. So we are hoping that we may get this kind of fossilized form of algae or biological signature on Mars, maybe next. We are not sure, but we are hoping that this is the conclusion. Actually, this is we need this kind of fossilized form on Mars to say yes, Mars was habitable, but it is habitable, but why we are not getting biological signature? So we must have to get this kind of biological signature until unless we cannot say anything. So this is that. This is a photograph of a stromatolite fossils. Okay, this is a cyanobacterial algae that is found on Earth since Precambrian. Okay, so if you get this kind of algae or this kind of fossilified material on Mars, then only you can say yes, life was there on Mars. But till date, we do not have any evidences. So what is the current objective? So current objective means we are now looking for a sign of life and investigate a Martian geological evolution. So right now, the science community are working on this part. Then we are exploring the natural resources of Mars. Okay, and demonstrate the human can live for extent and even permanent stay beyond Earth orbit. So this is one target. Okay, so scientists are working on this project. Okay, and advancement of space technology, of course, it is needed for this. Okay, then sample return, another one. Okay, so it's our second NASA's objective, that now they are looking for to return back the sample from Mars to Earth, and this is very important. World to work together. So now this is the collaboration, era of collaboration. So we have to work collaboratively. Okay, so this is the next target to work together. Okay, so thank you very much. This is my last slide. So we are like this geologist. Forest, this is the bed, but for geologists, we call this as a bed or bedding.
Thanks, so guys, the session is open for the questions. If you have questions, you can type in the chat, or you can directly ask by raising your hand.
Hi, Dr. Priyabrata. I want to ask a question.
Yes.
So my question is related to that. As we know, the chemical structure of Earth's surface and Mars surface is a little bit different. And the technology which we use here, like remote sensing technology or the hyperspectral imaging to find out the minerals, water body, and the greenery on the Earth, we are using the same technology on Mars. So don't you think that by using the Mars level aerial survey on the planet, rather than sending a short, small size rover on the Earth, if you will do the and survey of aerial survey of entire Mars planet by using hyperspectral imaging, so that could give the accurate result and a speedy result, because a single rover cannot complete the whole Mars surface. For that, you need millions of rovers over there.
Yes. Thanks for this question. Yeah, that is the thing. I think last this hyperspectral instrument, that is XRISM, that was sent by NASA, I think in 2005 or 10, between that time. Okay, so after that, they in Perseverance mission, they send one flying object called that's Ingenuity helicopter. Before that, there is no flying object. So they are now testing whether is it possible to do all this survey using a flying object. I think this is the first initiative. This is the first initiative taken by NASA to send that kind of helicopter, Ingenuity. Maybe next missions they may plan that kind of aerial survey. But yeah, it's a doable thing. I think it is possible. But in mass scale, like we can plan, like the space community can plan a kind of swarm. Swarm means that it's kind of not one single flying object, multiple, like the drone kind of thing. Okay, swarms of drone. So that can fly and map the entire province, one single province. So through that also we can try. So it is technological part. So I'm not that much into that part. See, I'm not a technologist, so I'm not sure whether it is possible or not. But if anyone can do this kind of thing, nothing like it. It's very it will give in-depth informations, which rover cannot do. Rover can travel only through a single path, a single direction. Okay, like this and like this. So there is some limitations. But if we put at least 3-4 this kind of helicopters or this kind of drones and attached with this hyperspectral camera for the survey, it's fantastic. Can do.
And my second question is related to that. If we got water on Mars, but we are not sure if we got water there that could be useful for human life, like you can used for drinking or farming?
Yeah, see, yes, Mars have water on the surface, but not in liquid form. Mars, right today, in present day, the water that is present on Mars either in form of gaseous form or in ice form. So there is no liquid water on the surface of Mars because of the thermodynamic conditions. Okay, so in that pressure, atmospheric pressure, but the liquid water cannot stable on the surface. Pure phase of liquid water. The impure phase of liquid water, like for example salt, if you brine kind of thing, that may be possible to stable on the surface of Mars. But pure phase of liquid water is not possible to stable on the surface of Mars. But NASA have developed in this Perseverance mission also. They have sent one instrument that actually try to collect the atmospheric water. Okay. And atmospheric vapor, like, okay, and how to make liquid water kind of instrument. So that is possible for, and we can use this kind of this liquid water for human exploration. Okay, that is also possible. That is also possible. You can just visit that Perseverance rover instrument, then we can easily identify, okay, what are the instruments they have sent for human missions. So this is one instrument, and also one instrument they have sent that is for oxygen. Okay, so how to generate oxygen from this atmosphere. Okay, there is another MOXIE, I think. Maybe I'm not wrong. For geologists, actually, yes, sorry. For geologists, actually, we can pinpointed the location where you can get a maximum amount of water on soil. So we can try for this thing. So for say in Martian dune or dune field, there are some specific locations where we have we know there are some specific locations where you can get more water or more like moisture on the surface. Like for example, if the dune surface or the soil surface is dipping towards pole, means or the North Pole or South Pole, so these pole-facing slopes are basically very prone to get moisture on the surface compared to the east and west, because these are the slopes where you get maximum sunlight. But the northern side and southern side dipping outcrops are good place where you can get moisture on the surface. So these are the locations where you can try to get. We can explore those regions for water, and these waters are actually mostly accumulate during the morning time. Okay, early morning. Okay, the kind of dew, but that is not a fresh liquid water. It's kind of frost. Okay, so you have to extract all this water through using the instruments. So these are that you can try, like if any robotic engineers, okay. They can do this kind of experiment in lab, okay, first, then can implement on field. Okay, next.
So we have one question in the chat section.
Yes. Sorry for also good. Yeah, this organic molecule actually detected by the rover actually have a suite of instrument inside. Okay, and this actually rover actually drill that surface, okay, the rock, okay, and collect the powder sample, and they took the powder sample to that instrument, okay, SAM, and this instrument actually have a gas chromatograph, okay. Through the analysis of this gas chromatography, then only they get to know the species of different organic molecule that is present on the soil. That not present in soil, that rock, a powder rock. Okay, so through that only they came to know the presence of organic molecule on the lake beds. And what we do, and can we do spectrometry of planets to get its constitutive? Yes, of course you can do spectrometry of the planet. Yes, you can do. So when will human go to? It's a big question. It's a big question. When human will go? Okay. So any other question? Human definitely human will go. Maybe by 2035, NASA is preparing to send a manned mission on Moon. Maybe after that, they are going to test this thing on Moon first. Then they will plan for another next mission, manned mission for Mars. So wait and watch. By 2050, maybe earlier, maybe later. I'm not sure, but it's a continuous process. Okay, so first, so it is not like that. Okay, let's go for Mars. No, it's not possible. First, we have to test the steps. Okay, and
sir, I have a question about Indian mission on Mars. So India is not planning to send any human mission over there. Then what is the purpose of the study of Mars for India and space program perspective?
The Indian first mission, the only one mission India have sent for Mars, that is Mars Orbiter Mission. That is a technological demonstration, or also have some suite of instrument, but mostly it is whether we can achieve the orbit or not, the Martian orbit, to test that technological thing. We have sent an orbiter on Mars. That is the first objective from our Mars mission, that Mangalyaan 1 mission. But now we are planning Mangalyaan 2. Okay, so ISRO is already already planning for our next Mars mission. Maybe we will announce soon when we will going for Mars again. And I'm not sure whether it will be again an orbital mission or orbital lander, because now we have achieved a landing, soft landing on Moon. So we may try for a soft landing on Mars also. I think it is needed now, because we already achieved a soft landing. So we have already demonstrated technology on Moon. So we can land comfortably on lunar surface. Now we can replicate, or we can try to land the Martian surface. So it's our expectation, but everything is dependent upon their plannings and their budgets, the technology, and everything. Yeah.
So like, how do scientists determine the age of Martian geological features, and what role does radiometric dating play in this process?
Yeah, radiometric dating means first, like the Martian meteorite that we can date easily in our lab, okay, because it's a meteorite samples. But for in situ, like the crop that present on the surface on Mars, it is very difficult, because we usually do a technique called crater chronology. See the orbiter images, like satellite images, we count on the impact crater, and by counting the size and all this density, okay, so that from that we can easily we can calculate the age of the province or the region. And for further down, like for say lander or rover, okay, so the rover actually carry one QMS, a quadruple mass spectrometer, inside that, okay, inside it, on the back of the rover, okay. So using that QMS also, they can easily date the material. For example, Curiosity have a QMS, and it has dated the lake bed around, I think, 3.7 billion years. They drill the material, collect the samples, powder sample, then collect the samples and analyze, okay, using radiogenic isotope. like potassium argon. I think they use potassium argon to date this rock. So that is possible, and it has been dated by curiosity and also perseverance.
So I have one more question. So
Please.
so in your like example in future Mars exploration, what technological advancements or like instruments do you like believe it would like greatly benefit geological research on the planet?
So it's depend upon which you belongs to from which called space agencies. Suppose if you're in NASA, your vision will be something different. But if you're in ESA or European Space Agency, their target is different. If you're in Japan, your target will be different. If you're in India, your target will be different. And also it depends upon the target area, means where we are going to land. That also it's very important. Based on the regional geology or the geological information that you would like to gather, on the basis of that you have to plan your instrument. Okay, so that is very important. So for example, suppose if you are going to land an area which is now mostly volcanic terrain. Okay, so and if you want to take a core sample, not this much core, 25 or 2.5 centimeter, you want a core for say 1 meter or 2 meter core to understand the subsurface information. Then you have to design that kind of instrument that can drill the surface up to 1 meter or 2 meter or 5 meter. Okay, so as per your requirement, as per your science objective, you have to design your instrument first. Okay, and this may be different. It may be opposite. Like first we have sort of instrument, then okay, we have this instrument. Now we have to plan our science. So that also can be possible. So it's like collaborative work. So scientists and engineers are working together. That's why. This is important because now this water, that availability, some people, we still believe that water can be present on the subsurface. Okay, so to detect that water, we need to drill the surface, and we need that kind of facility. Okay, especially for polar region, or if you are planning for landing the polar region of Mars. The polar region is mostly composed of this CO2 and water ice. If you want to explore those say that area, then your instrumentation, sort of instrumentation will be different. It is not like that our equatorial region. Okay, if you're planning to land in equatorial region, then your instrumentation will be different. So it's everything is depending upon your objectives, mission objectives.
So
Okay,
like one last question, just last question. So is there any like geological mysteries on Mars or something, unanswered questions about like Mars geological features, like you personally feel challenging, like personally, or intriguing?
Yeah, it's there are many, there are plenties. Okay, there are plenties. In which standard you are right now? You are in school?
Sir, 8th standard, sir. Sir, 8th standard.
Great. Oh, great. Then you just follow the popular lectures and science magazines and websites. Okay. Then attend, if possible, attend different workshops, also online virtual workshops. Okay. There people discuss on this long-lasting problems, like how Martian water was actually escaped, or maybe because Mars once had water on the surface. And what happened? Why at present there is no water, no liquid water on the surface? What happened after a certain period of time? So these are the big questions. Okay, so on which you can work, you can study. Okay, you can follow different lectures. You can collect some research papers that is available. Okay, you can download it, you can read it. But before that, I recommend you complete your education first, the basic education, basic science, physics, chemistry, and mathematics and biology. Okay, you continue this thing and learn some good tools and technique, like some codings, computer coding, and all this AI if possible for you. Then while studying all these things, parallelly you attend all these workshops and seminars, okay, so that you can get to know what is going on in this field of science. Then when you get the opportunity after your +2, then work on that direction. Okay.
Sir, I actually wrote a research paper, but I want to write the next research paper as geoscience on Mars. But I just need how can I get like information on it or something?
So these informations are the data that is the planetary data actually readily available on website, NASA's website, called PDS, Planetary Data System. Okay, it's a free data. Okay, anyone can access, or you can download all the images that is like curiosity image, perseverance images. Everything is readily available. Okay, you can just log in and download. No issue. Okay, if you want chemical data, it's available. Physical data, or everything is available in the website. You just have to log in that website and you can download it. Planetary Data System. It is available. Okay, even our Chandrayaan-1 data also available in Chandrayaan-2 as uploading. Okay, so all this planetary data is available on in website. Okay, so just log into PDS Geoscience node. Okay, there, and you can get all this info. But how to use the data? For that you need to know. You have to have a solid understanding of the subject. Then only you can interpret all these informations. So that is the basic learning. So first you learn all these things and learn how to use those data, then interpret it. Okay, but yes, of course, you should associate with some good scientist or good person who can guide you properly. Okay. And see, in our in where I am right now, associate Parul University. Parul University also is a newly established geoscience department. I think 4 or 5 years before established, and we are now offering a small project for our internal student to work in this planetary sciences. So if anyone interested, they can opt geology, MSc geology or BSc geology in our university, and can work on this domain, Earth and planetary sciences. Any other questions? Thank you.
Some people already sent their questions in messaging.
They can unmute and ask, no issue. Aditya, if you have any question, you can unmute and ask.
Yes, sir. Thank you for the talk, sir. My question is, there are two types of data collecting missions. One is the sample return modules, which are of course on bigger scale, and there are spectrometers like QMS on rovers. So which one is more feasible and which one provides more data?
Spectrometric data means it is hyperspectral or this remote sensing data, right? You're talking about. Sample return mission is of course important. Means that is the ultimate goal. We need direct sample. Like today, means I think last 2 weeks back we got samples from asteroid Bennu, right? Then asteroid samples, different Hayabusa in Japan have planned one sample return mission from Hayabusa. That is the main thing. We need a direct sample return, because after getting the samples only we can do plenty of analysis in lab. Okay, we have n number of facilities on Earth. Okay, so and chances of error will be minimum if you test the sample on our lab on the laboratory condition. But if you test the same thing on field on Mars, your error will be much more. So it's better to bring the sample on Earth and test it. But if it's not possible, then you can use indirect methods, spectroscopy method, and other like laser method. Okay, so that can get destructive and non-destructive method you can use for to get the geological informations.
Thank you, sir.
So we have one more question. Like, someone is pursuing BTech in computer science second year, so he want to switch his career from BTech in computer science to geoscience in masters. So is that possible?
You talk to that university, whether the university is going to take you or not. It's completely dependent upon the university. I think it is possible. In our department also, one fellow from physics, chemistry, mathematics, PCM background, he did his graduation on this physics, chemistry, mathematics. Then he joined geoscience in master level. So I think now the system is a bit open. Okay, so you can talk to that university and you can opt geology. No issue, I think. I believe. But it depends university to university. Some university ask, no, you need honors degree in BSc level. Then only you can enter masters in geology. We will not going to offer any other student. So it's depend upon university to university.
Okay, so one more question, like, according to you, what is the future, or if someone sees career in geoscience, what is the future in India?
Oh, geoscience future is very bright, and it means we have a lot of applications. Other than space sciences, okay, we have you can work on mining sector, mining mineral sector. We need geosciences, scientists for this mineral exploration. Started from mineral exploration, then production, mines production, and after the closing, the mine closure plan. So the entire this time period, we need a geoscientist to monitor all this thing, to do all this work. So mining sector is the main consumer of geoscience. Okay, then oil and gas industry, you can switch your career to can take the career for oil and gas. Okay, natural gas, and not only oil, then like new energy, like geothermal energy. Okay, so you can venture all this new area. Then geotechnical, like roadways, tunneling, dam construction. For that also we need a geotechnical person who know all these structures and the terrain. Okay, we have to do a lot of field work there. So these are the major domain where geologists work, and remote sensing and GIS, of course. Okay, so these are few area where you can work, and also if you are interested in research, definitely you are welcome. You can join as a junior research fellow. Now fellowships are increasing. Okay, so now if you want to join as GRF in any other science discipline, you'll get good amount of stipend. So that's also another career if you are interested in research. Then you can go abroad, study high, then other discipline also there. Okay.
That's one, got it. So I hope there is no more questions, guys.
Yeah.
Any question further? I suppose so. So thank you, sir, for this wonderful session, for enlightening. There is one question, I guess.
I am BSc Computer Science student, but I want to join ISRO. Can eligible as per? I'm not sure, Priyanka. I just checked that your ISRO's notification. Okay, previous year notifications, job notifications, or that kind of. So I'm not sure. But you have BSc in Computer Science. I think you will be eligible in some post. Okay, but just check once. Okay. Okay, thank you.
So thank you, sir. So let us conclude this session. Thank you, sir, for enlightening us in this wonderful journey from giving the perspective of geoscience on the planet Mars and guiding the students to pursue their career in the geoscience. So at last, I just want the audience to just turn on your camera so that we can have a snapshot with sir. Everyone just hurry up. So I hope you guys enjoyed this Wonderful. Okay, Sachin. Okay, so let's have a snapshot. Okay. Okay. So happy World Week, guys. Everyone just smile. Okay. Maybe soon we will be taking this screenshot from the planet Mars. Okay.
Sure. Thanks for inviting me, Arjit. Okay.
Thanks, sir.
Okay. Wish you all the best, and wish you all the best for the students also. Okay. You plan something big, plan design some field work or kind of off road kind of thing. Okay.
Yeah.
So
Sure.
we are geologists and we love to go for field work. Okay. So design that kind of activities. So
Sure.
space is now booming. Okay. So you design that kind of thing, hands-on activities.
Okay. Sure, sir. Definitely, sir.
Thank you.
Thank you, sir. So yeah, guys, thank you, sir. Everyone. Okay. Recordings will be uploaded. Okay.
Thank you, sir.